What specific problem does the proposed Muon optimizer aim to solve in the context of language model pretraining?
The proposed Muon optimizer aims to solve the problem of improving the compute time trade-off in language model pretraining compared to the widely used AdamW optimizer. Specifically, Muon seeks to enhance data efficiency while allowing for larger batch sizes, which facilitates faster training without compromising the model's ability to generalize from the same training data. By exploiting statistical dependencies between model parameters, Muon expands the Pareto frontier on the compute time trade-off, thereby increasing flexibility in resource allocation for practitioners. Additionally, Muon addresses the challenge of hyperparameter tuning at scale through the maximal update parameterization (MUP), which allows for effective hyperparameter transfer from smaller to larger models. Overall, Muon is designed to optimize both computational efficiency and training time, making it a more favorable choice for large-scale pretraining tasks.
How does the proposed Muon algorithm work? Please illustrate step-by-step how it updates the weights during training, including the specific transformations and considerations taken into account.
The Muon algorithm updates weights during training by employing a matrix-structured steepest descent approach with spectral norm regularization. The weight update is formulated as a transformation of the gradient, where the update rule incorporates momentum and weight decay hyperparameters. Specifically, Muon avoids explicit computation of the singular value decomposition, SVD, by utilizing the Newton-Schultz iteration, which allows for efficient updates without the overhead of SVD calculations. The algorithm maintains only the first moment, initialized to 0, and normalizes the updates to ensure that the RMS value aligns with that of the AdamW update, facilitating compatibility in learning rate schedules. Additionally, Muon is designed to be flop efficient, particularly in large batch training scenarios, by ensuring that the overhead diminishes as the batch size increases, thus enhancing its practical applicability in distributed training environments.
Can you provide a simple but illustrative example of how Muon operates in a training scenario, including the comparison with AdamW in terms of efficiency?
In a training scenario, consider a model with 500 million parameters being trained using both Muon and AdamW optimizers. When employing Muon, the training process can utilize larger batch sizes, such as 16 million tokens, while maintaining data efficiency, which allows the model to achieve a target loss faster than AdamW. For instance, as shown in the paper, Muon consistently requires fewer tokens to reach the same loss compared to AdamW, indicating a lower data overhead. This efficiency is further illustrated by the compute time trade-off plots, where Muon expands the Pareto frontier, allowing practitioners to allocate resources more flexibly. Thus, while both optimizers may have similar flop counts, Muon's ability to maintain data efficiency at larger batch sizes results in a more favorable overall training time and resource utilization compared to AdamW.
What are the practical benefits of using Muon over AdamW, particularly in terms of data efficiency and compute time trade-offs?
The practical benefits of using Muon over AdamW primarily lie in its superior data efficiency and enhanced compute time trade-offs. Muon maintains a more favorable data efficiency, particularly at large batch sizes, meaning it requires fewer tokens to achieve the same target loss compared to AdamW, which translates to reduced data overhead. This efficiency persists even as batch sizes increase, allowing practitioners to allocate resources more flexibly without sacrificing performance. Additionally, Muon expands the compute time Pareto frontier, enabling faster training times by effectively utilizing more devices while still achieving lower training losses at any given number of steps. Overall, Muon's design allows for a more efficient training process, making it a compelling alternative to AdamW in large-scale pre-training scenarios.
How has the effectiveness of Muon been validated or tested in the paper? What experimental designs or metrics are utilized to demonstrate its performance?
The effectiveness of Muon has been validated through a series of experiments that compare its performance against AdamW across various model sizes and batch sizes. Specifically, the paper reports that Muon consistently achieved lower training loss at any given number of steps and reached target loss faster than AdamW in terms of wall time. To analyze the compute time trade-off, the authors plotted ISO loss curves on a two-dimensional plane, measuring total training time to reach a target loss as a function of the number of devices and batch size, demonstrating that Muon expands the Pareto frontier of compute time efficiency. Additionally, the relative data efficiency of Muon was characterized by measuring the ratio of token consumption required to reach the same loss compared to AdamW, showing that Muon maintains its data efficiency even at larger batch sizes. Finally, the paper employed a telescoping algorithm for hyperparameter tuning, which was validated on a family of transformer models, ensuring that Muon's hyperparameter transfer properties were effective across different model scales.
What limitations or drawbacks does Muon have, and how might these impact its adoption or effectiveness in various scenarios?
Muon, while promising, has certain limitations that could affect its adoption and effectiveness. Firstly, it requires careful tuning of hyperparameters, particularly the maximum learning rate and weight decay, which can be challenging in practice, especially for larger models. Additionally, the implementation of Muon is described as naive, suggesting that there is room for optimization, which may limit its performance compared to more sophisticated optimizers. Furthermore, the empirical findings indicate that while Muon maintains data efficiency at larger batch sizes, it still incurs a higher flop overhead than AdamW, which could deter users focused on computational efficiency. Lastly, the reliance on the maximal update parameterization (MUP) for hyperparameter transfer introduces potential estimation errors, necessitating multi-scale tuning that could complicate its practical application across different model sizes and architectures.